Hi Allah. Today we'll continue the discussion of cache design and we'll discuss one more important topic, memory interleaving. So let us continue the cache design. In that we have seen that earlier video. So mapping is required. First of all, what is meant by mapping means the capacity of main memory is large and it is divided into some blocks B0 to BK, and this is my cache memory. This cache is also divided into some blocks which are called slots B0, B1, B2. So this 0 to K means K plus 1 blocks has to be mapped to any of these uh, slots or blocks in the cache. So this is called mapping. So mapping is the process of converting or translating the main memory block number to cache block number. So mapping is nothing but conversion which takes input main memory block number and converts into cache block number. So this is about mapping, and there are various techniques with the mapping. Before discussing, we'll continue that. We'll take some example of the cache and main memory. Let's assume there is a cache memory of whose size is 64 KB kilobytes, and you know that the cache contains some words. This word size is 1 byte. So how to understand this? 64 KB means 64 kilobytes and KB means, you know that, 1024 bytes. So KB can be written as 1024 bytes. So 1024 means 2 power 10 into 2 power 6. 64 is nothing but 2 power 6. So total of 2 power 16 bytes. So 2 power 16 into 1 byte. So how many locations, how many memory locations or memory words it contains means 2 power 16. This is the way of understanding. And next, I have a cache memory of 64 KB and the size of one word is 1 byte, and the block size. Here the important concept is some memory words are grouped into blocks, so it is important to know the block size. Block size is 4 bytes. What do you understand by 4 bytes? 4 bytes can be written as 4 into 1 byte. 4 into 1 byte is the size of one memory word. So you are grouping 4 words and forming one block. So you are grouping 4 words and each and forming a block, or otherwise a block contains 4 words. And so this is my cache memory of 64 KB of 1 byte memory words and 4 bytes cache. So can you guess how many blocks would be present in cache memory? So the total number of words is 2 power 16 bytes into 1 byte. 2 power 16 one word locations, 1 byte word locations are present in cache, and you are saying 4 into 1 byte is 1 block. So 2 power 16 minus 2 number of blocks, that is 2 power 14 blocks are present in the cache. So let me redesign my cache. This is cache, its size is 64 KB, it is 1 byte, and size of block is 4 bytes. And how many number of blocks? Number of blocks is 2 power 14 number of blocks. Now let's assume this is my main memory and it is in MB. Of course, now the main memory is in GB. For simplicity, we are saying that it is 16 MB. So how can you understand the 16 MB? 16 MB means 16 into 2 power 10 KB into 2 power 10 bytes. So 16 means 2 power 4. So 2 power 24 into 1 byte words. And how many blocks? Divided by 4 into 1b. It's 2 power 22 blocks. Now ultimately the main memory contains 2 power 22 blocks, and the cache memory contains 2 power 14 slots. So ultimately what you should understand, the cache contains 2 power 14 blocks, or you can call it as slots, and the main memory contains 2 power 22 blocks. So these 2 power 22 blocks has to be converted into 2 power 14 blocks. So 2 power 22 blocks has to be converted into or mapped. In a nutshell, we can say mapped into 2 power 14 blocks or slots. This is main memory, this is cache. So we need some mapping techniques over here. To understand the concept, we should go through some mapping techniques, but ultimately you should get an idea that why we need to do mapping, why it is required to do mapping. Means we have huge number of blocks in the main memory when there are less number of blocks in the cache memory. When the processor issues an address, that address contains the block number of the main memory, which has to be translated into or mapped into the block number in cache. So let us discuss a simple technique. The logic here is, let's assume I have to convert some big number to some smaller number. That is the goal, right? In the earlier case, 2 power 22 has to be mapped into 2 power 14. So we will take a simple case, that is, let's assume I have to convert 2 power 8 into 2 power 2. So what I can do, take the main memory block number. So let's assume 8 bits are required, right, in main memory, and here only 2 bits, block 0, block 1, block 2, block 3. So 8 bits means 0 to 2 power 8 minus 1 values will come. Remember, 8 bits 0 to 2 power 8 minus 1 values has to be converted into 0 1 2 3. 0 1 2 3 means 4. Can you guess what is the relation between 4 and 0 1 2 3? So if you divide any number by 4, the remainder can be 0 1 2 3. So what I do, for example, if you take any number between 0 to 2 power 8 means 256 minus 1 255, that has to be converted into 0 1 2 3. Now I hope you understand. Divide the number by 4. So the goal is take the main memory block number, perform mod operation with number of lines or number of slots in cache memory. So in the earlier case, what happening? The main memory can contain block number 0 to 255. This is main memory block numbers, which has to be converted into 0 1 2 3. This is cache block number. Let's take 125. 125 mod 4. How much it would be? 125 mod 4. Divide 125 by 4. 125 by 4. 4 3s are 12. And there would be remainder 4 1s are 4. The remainder is 1. So if you divide 125 mod 4 becomes 1. So this 125 is mapped to 1. 125 is the main memory block number and 1 is the cache block number. But see, do you understand this technique? So I hope you are understanding the point. The point over here is that 125 is the main memory block number. When you do mod with 4, you get result 1. So map 125 to 1. Let us take some other example. 145 mod 4. How much it would be? 145 divided by 4. 4 3s are 12. 2 5 4 6 are 24. Again remainder is 1. So the 145 block, 125 block, 135 block, 155 block, 165 block, like that 205, any number between 0 to 255 ending with 5 leads to 1. So all should map to 1. So it is not possible all of them to map to store in one block. Only one out of all these can be mapped. So this is the disadvantage with direct mapping. But management mapping is simple. It's a simple technique. So let's understand. It is one of the simple technique. The simplest mapping technique. This is the simplest mapping technique. Each block of the main memory maps to only one cache line. So that means these 125, 135, 145, they can map to only first block. They cannot map to second block in cache, right? So each block of the main memory maps to only one cache line, one specific cache line. Here you should have a word, one particular particular or specific cache. If a block is in the cache, it must be in one specific place. Yes, exactly. Is what he's mentioning here. If a block is in the cache, its place is fixed. But there are so many competing blocks in the main memory. Only out of all those blocks in the main memory can be stored in cache. And the formula to map a memory block to a cache line is that I is equals to J mod C. Here J is the main memory block number. J is the main memory block number. In the earlier case I said 125. Mod C is the number of blocks in the cache. What do you get? Cache block number. So see here, J mod C. J means main memory block number. C means number of blocks in the cache, and you get a result I, that is cache line number. That is, we divide the memory block by the number of cache lines, and the remainder is the cache line address. So this is about direct mapping. Now let's understand some few examples of direct mapping technique. So in direct mapping, shrinking our example to a cache size of 4 slots, and so the cache line contains only 0, 1, 2, 3, 4 blocks. The memory block, main memory 0, 4, 8. Multiples of 4 lead to first block. 1, 5, 9 lead to second blocks. 2, 6, 10 equal to third block. 3, 7, 11 lead to fourth block. So in general, if you generalize this, if C is the number of blocks in the cache, 0C, 2C, 3C, 4C, multiples of C leads to first block. Next 1, C plus 1, 2C plus 1. If we add 1 to the above series, it lead to 1. Next one, C plus 2, 2C plus 2. That leads to third block. C plus 3 leads to fourth block. So this is about direct mapping technique. With a simple example. So let's understand the pictorial representation of direct mapping. So here what we have, this is slot 0, that is block 0, block 1, block 2 in the cache memory, and it has some bits: valid bit, dirty bit, tag. So each slot contains keywords. Tag identifies which memory block is in the slot. I tell you, in first slot 0 can be there, 0th block, 4th block, 8th block, 12th block, multiples of C, that is 4 block. Which block is present is specified by the tag. Valid, set after block copied from memory. Once you copy the block content here, set valid to 1. Indicate that cache lines has valid data. So the dirty bit can say that there is no valid data, and dirty bit is used for write operation. Whether you performed any write operation on the particular word in the block, then you set to dirty blank. So this is about direct mapping technique. Next, understand some address structure of the direct mapping. So the address structure of the direct mapping says that there is an easy way to compute, that is J mod C, based upon the bits in the address we are trying to access. So the address is in three parts. Least significant W bits identify unique word within a cache line. W must be enough bits to address a specific word in the cache line. For example, this is the address issued by the processor. Processor issues this address, which is 8-bit address. 8-bit address means 2 power 8. Main memory capacity is 2 power 8 bytes. That is 255, 256 bytes is the capacity of the main memory. So this is an 8-bit address. So this 8-bit address, if the block size is 4 bytes or 4 words, then understand that if you know a specific block number, this block contains 4 words, 0, 1, 2, 3. So 2 bits are enough. With 2 bits, you can identify 0, 0, 0, 1, 0, 1, 1, 1, 1, 0, and 1, 1. So 2 bits are enough. So that's what last 2 bits are used to identify a word in block. But we should identify the block number. So least significant 2 W bits, in case here W bits are 2 bits identify unique word within a block in cache. Next, significant S bits specify which line this address maps into. S must be enough bits to address a specific line in the cache. For example, if we have 16 cache lines, that means, say, the cache memory, if cache memory contains 16 blocks and each block contains 4 words. For these 16 blocks, we need 16 can be written as 2 power 4. So 4 bits are necessary for identifying a block in the cache. Right? So a cache contains let's assume a cache contains 16 blocks. So it is important to identify the which block. For that we need 4 bits. And within that block we have 4 words. So it's 2 bits are enough to identify a word in the 4 blocks. Similarly, 4 bits are enough to identify a block number. And we have remaining 2 bits. So the remaining 3 bits used as a tag to identify a memory block. That means if the main memory capacity, let's assume, is some 4 into 64 kilobytes or 64 bytes, then you are dividing the 64 by 16. So if we again group this 64 divided by 16, how much you get? 64 divided by 16. 4. Identifying 4 uh, parts in the main memory. This parts contains blocks. Blocks contains words. So this tag is used to identify which part the block belongs to. So this is about direct mapping address structure. So this is used to identify word in the block. This is used to identify the block number in cache. 2 bits are used. Which block in main memory is copied over here. So this is about direct mapping technique. Next, direct mapping address. Similarly, direct mapping address for 64K cache example. 64K cache means 64 kilobytes, 64 into 2 power 10 bytes, 2 power 16 bytes, 2 power 16 different memory words are there in the cache, and if the block size is 4 bytes, 4 words, then 2 power 14 number of blocks will be there in the cache. So 2 words, because the block size is 4, 2 bits are enough. 14 bits to identify a block number in cache. Remember, there are 2 power 14 blocks. Here 2 power 2 words in the block. And remaining these bits are used to identify the tag. So given 24-bit address to access 16 MB, so the main memory capacity is 16 MB, and given 24-bit address, 2 bits identify the words, 14 bits identify the cache slot, 8 bit left for tag. No 2 blocks in the same line have the same tag field. Check the content of the cache by finding line and checking tag. And there are 2 special bits, they are very important. See, this is the main memory address, 14 plus 8, 22 plus 2, 24 bit, 24 bytes. Then what is this valid V and D? V stands for valid, D stands for dirty. So given a 24-bit address, 2 bits word identifier, need 14 bits to address a cache. Now we also need some valid bit and dirty bit. What is this valid bit and dirty bit means? Valid indicates if the slot holds a block belonging to a program being executed. Whether this particular slot holds the block belonging to the program being executed. Next, I have a dirty bit, indicates if a block has been modified. So right, this dirty bit is related to write operation, whether you modified the content of the word in the cache or not. So dirty bit indicates if a block has been modified while in the cache, will need to be returned back to the memory before slot is reused for another one, because if the program modifies the content of the word in a specific block in the cache, this has to be written back into the main memory. If dirty bit, D stands for dirty bits. If it is set to 1, then you need to write back the particular block or particular word in the block to main memory. So let us discuss some pros and cons of direct mapping technique. It is very simple. It doesn't require any hardware, extra hardware or extra uh, so hardware is not required, and it is very inexpensive because it doesn't require any hardware cost. Fixed location for a given block, this is the disadvantage, because if a program accesses two blocks that map to the same line repeatedly, cache misses are very high. This condition is called thrashing. So use this word thrashing. Thrashing means uh, if your program, the user program, tries to access the two memory blocks which leads to same uh, which can be mapped to same block number in the cache. In the earlier example, you have seen that 125 mod 4 is equals to 1 and 135 mod 4 is also 1. So value is same. But what happens if the program wants to access both 125 block and 135 block at the same time? So these two has to be present in the cache memory at the same time, which is not possible because they lead to the same value, that is 1. So only one of that can be present in the cache. So with this, what happens, there will be high number of cache misses. Remember, cache miss means if a word is not found in the cache, it is called cache miss. If the word is found in the cache memory, it is called cache hit. There should be very less number of cache misses, cache miss, compared to cache hit. But with this direct mapping, what happens, there are some chances of having more number of cache misses. Now we see other technique called fully associative mapping. The fully associative mapping scheme can overcome the problem of direct mapping scheme. Uh, you understand, right? The major disadvantage with the direct mapping technique is that it may lead to a concept called thrashing. Thrashing means the number of misses, cache misses, becoming high. So this is a problem. For to overcome this problem of thrashing caused by direct mapping, there is an alternative technique called fully associative mapping. So the fully associative mapping scheme can overcome the problem of direct mapping scheme. A main memory block can load into a main memory block. Here in fully associative mapping, a main memory block can be loaded into any line of the cache, which is entirely contrast to the direct mapping technique. So the both 125 135 can be present in the cache at the same time. Memory address is interpreted as a tag and word. Tag uniquely identifies the block of the memory. Every line in the tag is examined for a match. Also, we need a dirty and valid bit. But cache searching gets expensive. Why? Because we need some this fully associative mapping needs some extra hardware that can simultaneously examine all the tags for a match. Lots of circuitry needed. So when you say hardware, you required hardware, its cost would be high. Need replacement policies now that anything can get thrown out of the cache. See, in case of direct mapping, there is no requirement of replacing policy, but in fully associative mapping, yes, uh, we need to have a replacement policy because any block in the memory or main memory or physical memory can be mapped to any block in the cache. So we need some replacement policies, like we have seen some page replacement policies in virtual memory, like that. To replace a block in the cache, also we require some page replacement algorithms. Let us understand how associative mapping or fully associative mapping works. Remember, this is my main memory, and this main memory is divided into some blocks, and this is my cache memory, which is divided into 4 slots or 4 blocks, and which has tag, dirty bit, and valid bit. So the block can map to any slot. There is no specific rule that specific number of blocks should be only mapped to specific slot. Nothing like that. It can have any slot in, any block can be mapped to any slot in the cache. So it is maintained, then it is required to maintain which block. The problem over here is that which block is stored in the which slot. You have to maintain that, can be done using tag. Unlike direct mapping, we also have valid bit and dirty bit. A block can map to any slot. Tags used to identify which block is in which slot. All slots searched in parallel for the target. This is important. All slots are searched in all slots means all blocks are searched in parallel for the target. If the processor issues an address, take that address, and that last significant bits contains words, bits for words, next tag, right? So this tag is entirely searched in all slots are compared with the issued address in at parallel, like we have seen associative memory or content addressable memory. So the cache memory should be in CAM. CAM stands for content addressable memory. Cache memory has to be CAM in uh, fully associative mapping. required to have. So next we see an example of associative mapping. So what associative mapping do means, remember there is the main memory address is divided into two parts. One is to search the particular word and the remaining bits are called tag. These are used to identify the block in cache. So here 22-bit tag stored with each slot in the cache. No more bits for the slot line number needed since all tags searched in parallel. So 22-bit tag stored in each slot with each slot in cache. So that means compare tag field of the target memory address with tag entry in the cache to check for a hit. So what happened? If you are storing a particular word, particular block in the main memory, store its entire address in the cache. That is the logic in fully associative memory. And follow the technique of content addressable memory and search for a particular block number in the cache with the data itself. That is the logic behind content addressable memory. Least significant 2 bits of the address entry, which word is required from the block. Let's take this is an address. This is my address. Then left 22 bits. They are grouped in this part, except these two bits. Except these two bits, the remaining 22 bits are as it is stored in the cache memory using a technique called content addressable memory. So the last two bits are used for identifying a word in the block, like 00 means first block. So the disadvantage with this fully associative is that you need some extra hardware and you need extra time. So there is a fully associative, we need extra hardware, it may consume some time, whereas direct mapping is a simple. But the problem is that direct mapping we need some, there can be thrashing. Here the problem with the fully associative mapping, the problem with the fully associative mapping is that you need extra hardware, so the cost is high. The problem with the direct mapping is that there can be a concept called thrashing. So we have a new concept called set associative mapping, which is a compromise between fully associative and direct mapping. Here cache is divided into number of sets. Each set contains number of lines. Given a block, maps to any line in a specific set. So the thing is, you are dividing the cache into some sets. So a block can map to any block in that set. So use directive mapping to determine which set in the cache corresponding to set in the memory. Memory block could then be in any line of that set, and 2 lines per set. It is called two-way associative mapping. So they will group 2 blocks in the cache and call as a set. So what's happening here? I'm dividing the cache into blocks, right? B0, B0. Now group the blocks and call as a set. If I group 2 blocks as one set, it is called two-way set associative mapping. Something like that. There can be k-lines set associative mapping, like that. So this is about cache design.